Hello guys, this is CODEtronics team and we are going to present solutions for the Codeforces round 976 division 2. It was hosted by IIT Indore. So let's get started the solutions. I hope the question is visible on your screen. So this is the problem A of this Codeforces round. So let's go through the problem statement. You are given two integers n and k. In one operation, you can subtract any power of k from n. Formally, in one operation, you can replace n by n minus k to the power x for any non-negative integer x. And what we need to find is find the minimum number of operations required to make n equal to 0. Okay, so first of all, we should be clear that a solution will always exist for this problem because what you can think in layman terms is you can always subtract 1 from your n, so you're always going to have a solution in all cases. So in input we have number of test cases and each test case will contain n and k as described in the problem statement, and we need to output the minimum number of operations. So let's just try run for one of these test cases what we need to do. Okay, so I'll just quickly present things on a Google Doc for explaining it. Okay, so let's just say we have a test case of uh, 5 and 2. Okay, so n is equal to 5 and k is equal to 2. So the minimum number of operations to carry out for this test case is like if we have 5, we can subtract a power of 2 as we can take its square, right? So it will reduce to 4. Sorry, it will reduce to 1. And on 1, what you can do is you can take the power of 0. So it reduces to 0. So this will be your operation 1. Okay, and this will be your operation 2. So in this way, the answer for this question will be 2 operations because that is the minimum possible number of operations you can have. So the output here is 2. Let's try run for, let's say, 103. So this will be, let's say, test case 1, and let's say we take test case 2 of 103. So what you can do for 103 is you have to find out the maximum power of 3 which is just smaller than your n, right? So that you can subtract it, otherwise it will go to negative, and that's not what we want. So let's say we have power 3, then its square is 9, its cube is 27, its next power is 81. Okay, and its next power is going to be 243, which is greater than 100. So we will consider these powers. The largest smaller than 100 power is 81. Okay, so in operation 1 we will subtract 81 from 100, so it will produce 19. In operation 2, the next is just smaller power is 9. Okay, so we will subtract 9 from 19 and it will produce us 10. In operation 3, what you can do is we can subtract 9 again, so it will produce 1. And in operation 4, you can take 3 to the power 0, so you will get 1 minus 1 equal to 0. So the minimum number of operation it takes is 4. So the answer to this problem will become 4. Okay, so how are you to think for this question? Just okay. So how are we going to build up our thought process for this problem? So a basic idea you must be getting here is we have to subtract the greatest smaller power of k from n, right? For example, if we had 100, so we were compelled to subtract 81 from it, so that maximum number can be subtracted and it can be reduced to as small number as possible. Okay, so in each iteration, for each operation, we'll have to find out uh, the greatest number. So what we will be doing in our algorithm is what we'll doing in our algorithm is we'll have to find out first of all for starting value 100 what is the largest value. Let's say we found out for this test case that 81 is the highest value. Okay, now what we will be doing is we will just break down it backwards. Like if the work for 81 is done, we will check for 27. If the work for 27 is done, we'll check for 9. If the work for 9 is done, we'll check for 3, and subsequently we'll reach to 1, which will reduce things to 0 eventually. Okay, so what we'll be doing in our algorithm is, let's say, first of all, we'll have to look for an edge case here. And the edge case will be, what if k is greater than n? What do you think what will happen? If k is greater than n, whatever we will subtract any power other than 0, it will become negative, right? For example, if n is equal to 5 and k is equal to 6. So if you subtract any power of k other than 0, like for example, we have 1, we have 6, we have 36 and so on. If you will subtract any number other than 1 from 5, it will eventually give you a negative number, and that's not what we want. So what we'll be doing is we are compelled to use 1 at all times. Okay, so we'll have to use 6 to the power 0 at all times. So it's quite evident that the number of operations it will take is directly n, because you'll have to subtract 1 again and again until n is exhausted. So number of operations will get 1. So this is our the only edge case, and that's how we are going to not consider this edge case in our algorithm forward. Okay, so what we'll be doing is first of all check if uh, n is lesser than k. Okay, what we'll doing is directly just print out n and return from our problem. Okay, and if it is not the case, if n is greater or equal to k, what we will be doing is, let's say first of all we are in a hunt to find out the greatest smaller number than the n. Okay, so what we can do is just declare a variable j equal to 1. Okay, now you can take like a condition like while j is lesser than n. Okay, while j is lesser than n, what you can do is just multiply j with k. Okay, until you get the answer. And moreover, what you can do is, I think it would suffice this condition. As it gets greater than n, this loop will terminate, and eventually it won't take an infinite long time. All right, so now you find out, now you found out that what is the just smaller value than n. Okay, now what you can do is you can create another while loop, and you just need to consider when n is not equal to 0 until n becomes equal to 0, and you will run that while loop. And in that loop what you will be doing is just subtract the n such that there is no more requirement of that particular number. For example, we have 100, so how many 81s we need to subtract from 100 in order to get it lesser than 81? Okay, that's what we want. So what directly is convert n equal to n percentage 81. Okay, many of you might be thinking that we can also run a loop here and check up to how many iterations n is not becoming lesser than that particular number. All right, we can do that. We can do that. But the problem that will arise here is that will take a lot of time, and we are only permitted 1 second for this problem. So that will take a lot of time, and that's not what we want. It will give time limit exceeded error to you. So what we'll be doing is we will directly convert n equal to n percentage modulo j, and the number of operations that we need to find as answer, that will be equal to uh, the number of operations will be equal to whatever is the value of n right now divided by j. And it obviously makes sense, like for example 100 divided by 81 is 1, so we need one operation to reduce 100 lesser than 81 now, right? So that's how it's going to be. And furthermore, what you have to do is, once this is done, once the value of n becomes lesser than j, what you can directly do is, you can just reduce j by k, and we will do it until n becomes 0. So with the help of this while loop, you will be getting a value of ct, which will eventually be your answer for this problem. So that's how it is. One more edge case you will need to take care here about is, when you are checking this n is less than equal to k, you can also add on a condition that if k is equal to 1. Because if k is equal to 1, this loop is going to run for infinity and it will give you time limit exceeded. So that's another edge case you will need to take care about. And that's all for this question. It is an easier, it will be on easier side for this contest, and it just requires a one catch that you cannot run uh, a while loop. Even if you are running a 100 length loop inside this while loop, it will give a TLE. So this is strictly bound to time, and that's what is the beauty of this question. So that will be the solution for this first problem. Hello guys. So this is Codeforces round 976 division 2, and we are going to start discussion over the second problem. So I'll just quickly share with you the problem. Okay. So this is a very decent, nice question, and it does not involve much complex algorithms. However, it involves critical thinking about how you assess the test cases given in the problem and how you start developing your thinking. All right. So let's just go for the problem statement. Imagine you have n light bulbs numbered from 1 to n. Initially, all bulbs are on. To flip the state of a bulb means to turn it off. It is used to be on, and it turns it on otherwise. Okay, so we are just given n, uh, the number of light bulbs which are initially on, and by flipping we mean that if it is 1, we turn it to 0. Like if it is on, we turn it to off. If it is off, we turn it to on. Like if we have 1, then it is 0. If we have 0, then it is 1. Okay. Now what we have to do is, for each I is equal to 1 to up to n, flip the state of all bulbs j such that j is divisible by I. Okay. After performing all operations, there will be several bulbs that are still on, and your goal is to make this number exactly k. Okay, so many of you might be puzzled about this statement, what is happening here. So I'll just quickly give you a quick uh, illustration of what is being done here. Okay. Okay, so let's say we have any n, let's say n equal to 5. So what we'll be having is 5 bulbs which are initially on. So I'm keeping 1 for on and 0 for off. Alright. So what we are having is, we have 5 indexes. I is equal to 1, I equal to 2, I equal to 3, I equal to 4, I equal to 5. Okay, the statement says that, uh, just a second. The statement says that for each I is equal to 1 to up to n, flip the states of the bulb j such that j is divisible by I. Okay, so for each I, we have to flip the bulbs which are a multiple of these indexes. Let's say, for example, we have 1. So whatever is divisible by 1 will be flipped. For example, 1, 2, 3, 4, 5, all are divisible by 1. So we will flip the states of all the bulbs, right? So what we are having in I is equal to 2 is, thus we will carry on this previous state and flip the bulbs according to the indexes which are multiple of 2. Okay, so let's say we have 2, we will flip its value. We have 4, we will flip its value, and 5 will be left untouched. For I is equal to 3, what we will be doing is, we will flip the state of the bulb of I is equal to 3 4 and 5 will be left untouched. 1 and 2 are obviously lesser than 3, so we will not talk about them. Okay, for I is equal to 4, what we will be doing is we will just switch the value of I is equal to 4 because 0, 1, 2, 3, 1, 2, 3, and 4. Okay, so this is 4. We will switch its value back to 0, and this will be left 1. 2 and 3 will be left 1. 1, 4, and 5 will be 0 now. Okay, for I is equal to 5, we will carry on the previous state and we will flip the value of I is equal to 5 equal to 1 because 1, 2, 3, and 4 are less than 5 obviously. So this will be the final state of the bulbs after fifth iteration, and the number of on bulbs are 3 here. Okay, we will just move on with the problem statement now. Just share the problem statement again with you. Okay, so after performing all operations, there will be several bulbs that are still on. Okay, and what we need to find is my goal is to make this number exactly k. Find the smallest suitable n such that after performing the operation, there will be exactly k bulbs on. Okay, we can show that an answer always exists. Alright, so initially, what did I say to you? I told you that we have to assess these test cases very carefully in order to reach out a perfect solution for this problem. Okay, so let's say we have to find out the minimum n, okay, for which the given k number of bulbs are appearing. So we will be having possibilities that more than one n are giving you same value of k. So you will be having to find out the least value among them. Okay, so let's just go for different values of n and find out what are the different values of k it can produce. Okay, so I'll just quickly try run things with you for a better explanation. Let's say we have n is equal to 1. Okay, so what we'll be having is an initial bulb on and it will be switched to off. Why? Because I is equal to 1 iteration will be happening, so it will turn it to off. For n is equal to 2, we will have two bulbs, initially 1 1. For I is equal to 1, both will become off. For I is equal to 2, the second bulb will get on. Okay, so here the value of k is 0. Here the value of k is 1. Okay, for n is equal to 3, what will be happening is we have three bulbs 1 1 1. We'll switch them off using first iteration. We will use I is equal to 2. Okay, then we will use I is equal to 3. So here the value of k is 2. Okay, for the next iteration, let's say we have n is equal to 4. We have 4 bulbs. By using I is equal to 1, we reach out to this. By using I is equal to 2, we reach out to this. By using I is equal to 3, we reach out to this. By using I is equal to 4, we reach out to this. Okay, so one thing you can observe here is the value of k is 2 in 3 as well as 4, right? So one thing to note down is if we have to report an answer for k is equal to 2, we will select n is equal to 3 and we will not select n is equal to 4 because 3 is the smaller one, right? So that's how it is. I'll just give you for n is equal to 5, I just told you before that it's going to be 0, 1, 1, 0, and 1. And for that k is equal to 3. And if we are to report the minimum value for k is equal to 3, that will be 5. And if you remember, we are given a test case where the value k is equal to 3 is given and its value is given as 5, right? So that's how you have to choose the pattern which is forming in this problem, and you have to search for a solution that way. So if you go on and write different values of n and their different bit values, what you will come to know is that for all the square numbers that are appearing, for all the square numbers, let's say we just let me just give you some more values so that it becomes more clear. We initially have when is equal to 6, we have 6 bulbs. Then using I is equal to 1, then using I is equal to 2. Okay, then using I is equal to 3. I is equal to 3, right? So 1, 2, 3, 4, 5, 6. Just notice that for I is equal to 1 it became 0, for I is equal to 2 it became 1, for I is equal to 3 it became 0. Why? Because this is the sixth index. Okay, so for I is equal to 3 also it will be flipped. For I is equal to 4 now I am going to do, for I is equal to 4 it will become 0 and this will remain unchanged. For I is equal to 5 this will be the case. For I is equal to 6 so here we are obtaining k is equal to 4, right? Okay, so one observation that will come out if you go for more iterations like n is equal to 7, n is equal to 8, n is equal to 9 and so on, that for the all the square numbers that are appearing before that value of k, it is getting uplifted. Like for example, if I say find out for k is equal to 4, okay, so the number of square numbers that are behind k are 1 and 2. Okay, 1 into 1 equals to 1, 2 into 2 equals to 4, 3 into 3 equals to 9, which is greater than 4, so we will not consider that. Okay, and these two are uh, the correct, I mean the smaller square numbers before k. Okay, so you will just observe that uh, number of squares before k is equal to 4 are 2, and if you uplift the value of k by that particular value, you will reach to n is equal to 6, and that is your required answer. Okay, but one catch here that arrives is, what if the incremented value is greater than a square number itself? Okay, let's say for example we have k is equal to 7, right? Number of squares before k is equal to 7 is equivalent to k is equal to 4. Okay, 1 into 1, 2 into 2. If you increment k by 2, okay, k plus equal to 2, it makes it 9. But 9 is itself a square number. So if you are encountering a square number again, what you will have to do is you will have to increase k by 1, because a square number is appearing again on incremented value. So what you will get after that will be your final required solution. Okay, so the first of all what we have to find out is the number of perfect square numbers before that particular value of k. Okay, and what after that is what we have to check is increment the value of k by that number, and then check once again if it crosses the value of next square number. If it does, just increment the value of k by 1. The value thus obtained will be the final solution for this problem. Okay, okay, so first of all, what we have to think about is how we can find the number of squares before that. Okay, let's say we have any arbitrary k, let's say 15, and you have to find out number of square values before k. So what you can do is you can directly take x is equal to sqrt of k. Okay, it will directly give you an integer which will be lesser, which will be giving you the answer to the problem that how many square numbers are before k. Okay, the value to this will be 3. That will include 1, 2, and 3. Okay, because 4 into 4 is going to be 16. So directly by this logic, you can find out number of square values before k. Okay, now I will just give you a try run over a test case to ensure that our solution is going in the right direction. Let's say we have test case where the value of k is 8. Okay, so the number of square values before k is equal to 8 is like 1 into 1, okay, and 2 into 2. 3 into 3 is going to be greater than 8, that is 9. So what we are doing is, let's say int x is equal to sqrt of k. Okay, so what will n give you? N will x will give you 2. Okay, now we will increment k by 2. Okay, then k, sorry, k by 2, k plus equal to x, so k becomes 10. Just check the if it crosses the next square number, right? Since x was equal to 2, so we will have to check for x equal to 3. Check for x equal to 3, right? 3 into 3 is equal to 9, which is smaller than 10. So in such case, what did we have this second rule. We have to increment k by 1. Okay, and once you increment k by 1, it increases to 11, and for sure you can say that 11 is not greater than the next square number, and this is going to be valid for all the cases that on incrementing 1 it is not going to cross any other square number. You can manually check, and it does not really need to be checked. It is quite logical that by just incrementing 1 the next square number cannot be traced easily. Okay, so that will be a final answer, and the value is given as 11 in the output. I'll just show you the output for this test case also. See, for the value of 8, we have the value as output 11. So that's how this is. The question involved critical thinking, where you had to manually run things on different test cases and just observe a pattern. Okay, just observe a pattern. Write down different test cases for n is equal to 10, 11, and just find out the pattern that is forming. That there is only one bump when the square numbers arrive. So the number of square numbers appearing before the value of k or uplifting the value of k. So that was all for this problem. This solution is accepted, and that will be the end of this video. Thank you. So hello guys. So we are here with the third problem of Codeforces round 976 division 2, bitwise balancing. So I hope you people have attempted this problem. And this is a beautiful problem when we talk about bit manipulation. Many of you must have been a little, uh, thinking about that, what is bit manipulation and all that. In further classes, we will be covering this topic. But if you have even a fair idea, this problem is solvable for you people. Okay, so let's go with the problem statement. You are given three non-negative integers b, c, and d, and we are to find a non-negative integer belonging to 0 to the power 2 to the power 61, such that a or b minus a and c equals to d. Okay, where this and this are bitwise or as well as bitwise and operations. Okay, and if such an a exists, print its value, and if there is no solution, we directly need to print -1. Okay, and one more condition: if there are multiple solutions, you can print any one of them, right? Okay, so what we are given is the value of b, c, and d, and we have to print a single integer value. If answer exists, the value of a, which satisfies this equation, and the value -1 if no solutions exist. All right. So what is the first intuition that you can think of in this question is, you can directly run a loop from 0 to the power 61, 2 to the power 61, and just manually check for all the values. If this condition is holding, we can directly print the value of a, and if for the entire loop the value does not exist, we print -1. But obviously that problem is not going to be accepted. Why? Because the range is too much, too high. So running a loop greater than greater than 26, 27 will obviously fetch you a TLE, time limit exceeded error. So you will have to find out a different optimized solution for this problem, which satisfies our need for this problem and does not give us a time limit or memory limit exceeded. Okay, so I will just take some test cases and explain you what is happening in this problem. Let's say we take the test case of 10, 2 and 14. Okay, 10, 2 and 14 where B is 10, C is 2 and D is 14. Okay, so the problem reduces to that we have to find out and A says that A or 10, A or 10 minus A and 2 equals to 14. Okay, so that's what you have to do. Alright, so what we will be doing is, since this is a problem of bit manipulation, we'll have to find out for all the bits what conditions we need to implement so that for that particular A, this condition is going to hold for us, right? Okay, I would like to also explain you that why this intuition of bit manipulation is appearing in my thought process. This is because this question involves bitwise operators. Okay, we have or, we have and the next thing is the constraints of this problem is that your BCD lies between 0 to 118. Okay, so a single for loop will not be solving a problem in this question. Alright, so we are left with the only choice of using bit manipulation in this problem. So that's how you get the intuition of why I should be thinking about bit manipulation angle for this problem. Alright, so uh, what you can do is first of all expand these B, C, and D into its binary structure, binary form, and then evaluate over what conditions should we implement on A so that we get the required results. Alright, let's say for 10, the binary structure will be 1010, right? For 2, it will be 0010. I'm keeping the number of bits same for better understanding. For 14, what we have is for 14, what we have is for 14, it is 1110, right? So if you will assess properly, with 10, what we have to do is OR operation, OR operation of A. For 2, what we have to do is AND operation of A, right? And this is the right hand side. Okay, so just have a look over what we do in OR operations. Like if a bit is set already in 10, okay, no matter what you do with A, the bit is going to stay set. Alright. What we do with AND is if a bit is set in one of the operands, if the A does not have it the bit set for that particular bit, it will set to 0. So necessary condition is both bits should be set to get a set bit for the operation. Alright. And in this, either of A or M should have a I will just use a generalized form. B should have a set bit. Okay, so that's how uh, OR and works in bit manipulation. Okay, and this is the required result for D. So what you will do is in this problem, first of all, focus over the maximum limit of binary digits that you can have. Like for example, we are given that A belongs to 0 to 2 to the power 61. Okay, so what you can have is you can start from the 61st bit and reach out to 0 and eventually use these conditions that uh, if the bit is set in this and it is not set in this, then what happens to the right hand side? Okay, so let's say for this problem 10, 2 and 14, what we have to find out is, let's say we have many bits coming out from left. Okay, we reach to somewhere. 1010 for 10. Okay, we are ORing this thing with A. We are subtracting with, let's say, many bits coming from the left. Then 0 0 0 0 0 0 for 2. We are doing AND with A, and we want to make this equalize to many bits coming from left, 0 0 0 and 1110, which equals to 14, right? So just observe this thing, that the fourth bit from the left on the right hand side is 1. Okay? The fourth bit from the left in B is 1. Okay, so it's your responsibility to keep this bit set to 0. Otherwise, if it is 1, the 1 and 1 bit will cancel out each other and it will yield a solution of 0 on the right hand side. Alright, so it should be 1 here and 0 here. Okay, similarly, this bit is 1 on the right hand side, the third bit from the right. The third bit from the right here is 0. The third bit from the right here is 0. Okay, so you will have to set this bit to 1 and keep this bit 0 here. Okay, in order to yield the bit 1 or the third bit on the right hand side. Okay, now observe that the next bit is 1 here. Okay, and the second bit is 1 here as well. Just a second. 10, 2. Okay. So what you have to do is, this is 1 and this will going to stay 1 because there is an OR operation, and this is 1. So uh, by any means you have to set this bit to 0, so that 1 minus 0 can be 1, and 1 minus 1 should not yield 0 here because it is 1 here, right? So you will have to keep the second bit of A equal to 0 so that it becomes 0 and it stays 1. Okay, so this is how you have to manipulate your A in such in bits. Bitwise, you have to set A such that if it is set here, it should be 1 minus 0 for all the bits. Okay, so let's say for the fourth bit, what did we discuss? That A or B should be should be 1 and A and C should be 0. Okay, for the third bit, so we will see for the third bit what is happening. Third bit is also 1, so this condition again holds. Okay, for the fourth bit, for the second bit also this condition should hold, and for the first bit, since both were 0, these both can be either 1 or these both should be 0, right? So you can opt for any of the conditions since we are to report any possible solution. This is a negligible case you need to consider. Okay, so what we will do is we'll start from 61st bit, we reach out to 0, and we implement these conditions like the way we try run here, and we have to find out the solution to this problem. Okay, so what we'll be doing is we will run a loop variety as equal to 61, I greater or equal to 0, I minus minus. Okay, minus minus. Alright, and we'll just consider an answer. Let's say I give it name as A is equal to 0. Okay, the first condition that we will have to think is if D is set. Okay, and one more thing, how do you check that if a particular bit is set or not? Alright, so for checking that, what you can do is directly use AND operation, like D and 1 and then left shift I. Okay, so what this will give you is that if D has a set bit and it is undergoing with AND operation with this, then if it is 1, if it returns true, then that would mean that D has a set bit for that particular value of I. Okay, so if D is set and B is also set. Okay, if D is set and B is also set, so what you have to do is you should keep 0 anyhow you should keep 0 over C and A. Okay, so what you have to do is directly go for, I mean, you need not do any operation for that. You can directly keep A plus equal to 0. Okay, if C is also set, if B is set and D is set, let's say we check over the condition if C is not set. Okay, if D is set and B is set and C is not set, we need not do any operations. We also need to consider a condition where B is not set, right? If D is set and B is not set, okay, B is not set. B is not set. Okay, so for in that condition, if C is also not set, then we have to add A plus equal to f shift time. Why? Because we need to set B or A. Okay, C and A will stay unset because C is not set. So I'll just keep that condition here. If C is also not set, we'll implement this condition. Okay, we'll just keep this in else if. Okay, so we have checked out for one condition. The next condition will be if B and C is set and D is not set. Okay, next condition is if D is not set, okay, and B and C are set, then what you have to do is say if B and C are set and D is not set. So what you have to do is you'll have to purposefully keep C and A as set. So you'll have to include that in your number A, because if it is 0, C and A will turn to 0 and 1 minus 0 will turn to set bit 1. But we have the condition D is not set. So you have to purposefully keep A is equal to that particular set bit should be 1. Alright. So that is the second condition that you have to check whether if D is not equal to 0 and B and C are set. Okay. The next condition that you have to think about is if B is set and C and D are not set. Okay, I'll just quickly copy this. That if B is set and C and D are not set, D is not set, B is set and C is not set. Okay. So what is happening in this condition is C is set, okay, B is set and D is not set. So what you have to do in this problem is you cannot obtain a solution now, because for sure the condition is going to arrive where uh, B or A is going to be set, right? And since C is not set, C and A will give you unset bit, and set minus unset will give you on the RHS as set. However, D is not set as given. So what you have to do is just quickly print -1 because no solutions exist now, just written out of the function. So this is a test case where solution is not going to exist for us. Okay. And the last condition that remains is if B is not set, C is set and D is set. Okay, I'll just write that down. B is not set. Okay, B is not set. C and D are set. C and D are set. Okay, so what is happening here is B or A, it can either be set or unset. Let's say we take a generalized case. Okay, C is set. Okay, so if you set A and C will be set. If you all right. Okay, let's say we have a condition where A is set. Okay, then what will happen is A and C is set. Okay, if A is set, then B or A is going to be set, and then set minus set will produce unset. But we are given the condition that D is set. The second condition that you can think of is if A is not set. If A is unset, okay, then A and C will be unset. And since B was not set, this is also going to be unset. So unset minus unset condition will arrive, which always means unset condition. But D is given set. So in this, we get an error, like we are not getting a set bit on the RHS. So we'll have to produce -1 on the output as solution because no solution exists on that particular condition. So these are the four conditions which you'll have to carry out in order to produce your answer to this problem. I'll just keep that in one window. Okay, so this is how this problem has been thought, and this is not a very tough problem to be honest, but it involves thinking like how you are going to think in bits, how each bit is affecting our solution, and how we are building up A in order to satisfy the demands of this question. So this is all for this problem. It involves complex, not so complex, but a decent bit manipulation problem. So that will be it. So yeah, that's it for this video. I wish it is.